Okay, thank you. So this work was done with my group, Gopi Krishna and Muralidharan at Macquarie. Peter Rohde, who used to be at UTS, then moved to the company BTQ, and Peter is here, somewhere in the back, if you want to talk to him. Deepesh Singh at University of Queensland, and Boshang Fu, who was an undergraduate student at University of Melbourne. I just wanted to, he's currently moved over to Cambridge, but I just wanted to point out that I wasn't able to fund him on an SQA undergraduate scholarship because he's Victorian and not New South Welsh. So just to connect back to what Peter was talking about earlier, this is kind of an example where the National Quantum Collaboration Initiative could be useful. And then also some colleagues at BTQ, which is a quantum security company. How did I get back to that? Yes, okay. So proof of work is a mechanism used to choose which of miners on a network, a communications network, are allowed to be rewarded for the lucrative task of verifying a proposed block of new data. So this is used for communications in a distributed sense where you don't have a centralized authority. And the most common known example is blockchain applications. And the way it works is that you propose a problem that depends upon a proposed block data. And the problem involves inverting a one-way function. So you've given a function f, and you're given an output y, find the preimage x. And so you want such problems to be hard to solve, but easy to check. And an example of this is hashing. So for example, if I apply the hashing function to this sentence, the quick brown fox jumps over the lazy dog, I get this output, which just looks very random. And if I change just a single letter in that sentence, I get a completely different random output. So it's something with high entropy, and also it's collision resistant. So you don't have you're very unlikely to find two preimages for the same output. And this is used extensively in blockchain, where you have some header information about a proposed block of transaction data, as well as information about the previous block. And then you have to search over some random string called a nonce until you find a hash whose output is less than some number. And if you find that, you as a miner win some reward, and that block is added to the blockchain. Now, there's actually a prehistory for this. This goes back to an attempt to fight spam back in 1992. And the idea was to make senders of emails perform some computational labor before they could send an email. So you'd have a time and date stamp, a recipient's mail address, and some random string you'd have to iterate over until the hash of all that information was below some certain number. And if you received such an email, you could quickly check that, in fact, they did do the labor. And this would be trivial if you're only sending it to a few friends, but if you're spamming hundreds of thousands of people, then it becomes costly. Well, proof of work is used frequently in a lot of cryptocurrencies. Right now, or recently, this is about proof of work is a market capitalization of several $100 billion US. And I did want to point out that the number 6 cryptocurrency that uses this consensus mechanism, called Caspa, has actually thought about ways to make it more energy efficient using something they called optical proof of work, which is using a photonic mesh-based matrix vector product introduced in the middle of the mining protocol. So they actually have designed their algorithm so that you could speed things up and make things more energy efficient by having classical states of photons go through a photonic network to solve a problem. So people are thinking about this in the physics context. And the reason they're doing it is because proof of work is very energy costly. These machines which do hashing are now extremely fast. So this is just an image taken off of Amazon. This Antminer, which is an ASIC device, an algorithm-specific integrated circuit, can do 166 terahashes per second, which is insanely fast. But it's also very energy intensive. This is running at over 3 kilowatts. A lot of people around the world are running these things, and it's draining a lot of the world's energy supply. So the electrical energy consumed by the Bitcoin network is exceeding around 22 days of an average US household. That's for a single transaction. And last year, the Bitcoin network consumed the equivalent electrical energy of the country of Sweden. So this is clearly not a sustainable method to do transactions in a distributed manner. A second issue is that this is not quantum future-proofed. If you think of a future where we have ubiquitous quantum computing, or at least access to such devices, then you can do things like Grover mining, where you can sample over lots of proposed nonces to solve this inverse hashing problem, and you can get a quadratic speedup. Now, this would not be likely to help at all until many decades from now, but nonetheless, it breaks one of the requirements of a proof-of-work consensus protocol, that it should be progress-free. That is, the probability to solve the problem should be independent of prior work. So it should scale linearly with the time spent. And in fact, quantum computers introduced into this because you can solve things in superposition and have partial progress. You could actually measure your register before you finish the computation and have some chance of succeeding. In fact, there's a Nash equilibrium strategy, which is one which optimizes over having a probabilistic measurement strategy, which will introduce fluctuations in the verification time for the blocks. So we propose a different proof of work problem using boson sampling. And the idea is to encode the input of the problem, that it will include information about the block header, as well as the previous block, into an input permutation of n photons into m modes. Then it goes through an interferometer circuit described by a unitary U, and then you perform measurements at the end. So the output state is just this linear transformation applied to the creation operators acting on the vacuum state. And this is then a superposition over multi-photon output states with some amplitudes. The number of terms in this superposition is exponential in the number of photons. And each particular amplitude is proportional to the permanent of a matrix formed out of this unitary. So that's the essence of boson sampling. And the reason why we want to fit this into a proof of work consensus is that this is a problem that's hard to solve, particularly for classical computers. So the output distribution will depend on the amplitude squareds, so it will depend on these permanents. And the permanence is something that is very hard to compute. It's in the complexity class Sharp-P hard, even for a multiplicative approximation error. This is in contrast to a determinant, which has these -1 signs to the parity of the permutation on the matrix. And that's in the complexity class P. And that's just because the determinant is invariant under similarity transformations, whereas the permanent is not. It's only invariant under permutations. So boson samplers can't output individual permanents. We don't get a shortcut on complexity classes. But the output distribution cannot be efficiently approximated by classical computers. So I'm going to talk about the difference between doing boson sampling on a classical machine versus a quantum machine, show how it's faster, and then see how we can integrate that into a protocol. The classical sample rate, that is, if you wanted to just grind out a computation of permanence to sample from the boson distribution, is given, by basically, it's given by the best known classical sampling algorithm using Clifford and Clifford hierarchical sampling, which takes about, on average, 2 permanent evaluations per sample. And then each permanent can be computed using Reiser's algorithm, which scales like 2 to the n, where n is the number of photons times a factor n. And then you can get estimates for the time to perform these operations either on a single core Xeon processor, for example, or a supercomputer. The quantum sampling rate is determined by the bare photon generation efficiency, the coupling efficiency, and the detector efficiency, as well as a single photon source rate, and it's also dependent upon the beam splitter transmission probability. So there are finite errors that can occur in these things, and here we're going to assume these specifications, which are highly optimistic but not insane. These numbers have already been reported in the literature. And let's just see what we get as a comparison. So here's a speed up, the quantum sample rate divided by the classical sampling rate on the y-axis as a function of the number of photons, which you could say is determining the difficulty of the problem. So you start to be, for these specifications, you start to be faster than the single core processors at around, over 12 or so photons, and then you're beating the supercomputer at around 20. If you had worse specifications, it would just push these curves out a little bit, but at some point you'll still do better. Now what's interesting is the energy cost. So if we take the dominant energy cost for the boson sampler to run a cryocooler at say around 1.5 kilowatts, and you compare that to the energy cost for the single core processor or the supercomputer, you see there's a dramatic savings. This is a log scale here. Green is what the cost is for the quantum boson sampler, and then blue is for the supercomputer, and red is for the single core processor. So once you're past 12 or so photons, you're starting to get an energy improvement over classical simulators. Well, we can integrate this into a protocol. So here's how it works. A transaction is created on the network. A new block representing the transaction is created. The new block is sent to every node in the network, and all nodes stake tokens to participate. Miners implement boson sampling for a predetermined amount of time with an input state that depends upon the block header. And then they commit their samples. That is, they make a hash of them and then send them to the network. All contributed samples are then combined to create a net sample set, and these are binned according to a strategy stipulated by a random beacon. So there's some random number generator that's known to the network. It spits out a number. From that, you can determine a binning strategy, which I'll describe in just a minute. And then following validation, all honest verifiers in the network are rewarded for their proof of work and have their stakes returned. Dishonest verifiers are penalized via loss of stake. And then that block is added to the blockchain. So I'm getting low on time here. 1 minute or zero? Zero, OK. Well, let me just refer you to the paper and just state that using, I'll just pull up the conclusions here. Yeah, the typical Gavin talk, I know, sorry. You can translate an essentially useless problem, which is boson sampling, into one which is useful to prove you've done labor. And it works because you can validate a coarse-grained version of boson sampling known as mode-bin boson sampling. And then this will reward honest players who actually are doing the labor and penalize those who are cheating by producing false samples. And so we're working with BTQ to see how to implement this in some real devices. Thank you.
Thank you very much, Gavin. Yeah, maybe Gerard?
Could you say a little bit about how we work with Gaussian boson?
Yes, thank you. In fact, it becomes easier. If you use boson sampling, that's Gaussian input states, that is squeezed vacuum states, then in fact, the mode-bin distribution can be determined by a characteristic function, and that characteristic function has points which can be computed exactly using a determinant of a submatrix. So that's something we're looking at now.
If we could all thank Gavin again.